On the floor of a modern Indian factory, managers face a recurring operational choice every single day: automation versus manpower. Mainstream discussions typically frame this as a simple, hostile contest between human workers and machines. That framing fails to capture the technical reality of how industrial operations are actually designed. To understand how these systems function, we must look past the rhetoric and view the production floor strictly through the lens of systems engineering. The core debate centers on choosing between two distinct competing control architectures to run a plant. The first architecture relies completely on programmed intelligence. It uses rigid mathematical design to relentlessly eliminate any operational variability. The second architecture relies on human-driven heuristic experience. It is designed to rapidly manage and adapt to high-variance scenarios. The future efficiency of Indian manufacturing depends on how accurately plant managers map operations to these two distinct models. To see how that mapping works, we first have to deconstruct the exact mechanics of an automated ecosystem. In strict engineering terms, factory automation is a closed-loop deterministic ecosystem built to execute operations with minimal human intervention. This ecosystem is constructed using a specific set of tools: robotic actuators, AI-driven logic, PLCs, and SCADA platforms. Consider the operations of an extrusion line in a modern cable manufacturing plant. To produce a flawless cable, the system must maintain tight control over strict physical parameters: the temperature of the plastic, the speed of the line, and the precise insulation thickness. This diagram illustrates how a closed-loop control block manages those parameters. In the input phase, sensors continuously monitor the physical environment to gather real-time data on heat and velocity.
That data feeds directly into a programmable logic controller, or PLC. A PLC is a ruggedized industrial computer that processes sensor inputs against mathematically rigid, pre-programmed rules. In the execution phase, the PLC instantly sends direct, calculated commands to physical actuators, like valves and motors, adjusting the process without requiring human permission. These three steps, sensing, processing, and actuating, happen continuously, fractions of a second apart, locking the machinery into a specific state of operation. The engineering goal of this deterministic loop is to eliminate variability, ensure exact repeatability, and guarantee precision across millions of product cycles. Sitting above this physical loop is the SCADA platform. SCADA, which stands for Supervisory Control and Data Acquisition, is an overarching software architecture used to monitor and manage industrial processes. It operates as a supervisory layer, providing plant engineers with a real-time dashboard to track the health and performance of the deterministic loop. Under static, predictable conditions, this closed-loop ecosystem functions flawlessly. It calculates and adjusts far faster than humanly possible. The primary friction point for advanced factories occurs when the production floor requires a sudden, unprogrammed shift in those static conditions. In industrial operations, this is known as a manufacturing line changeover, a high-variance event. A single changeover forces the system to confront multiple overlapping variables simultaneously. Molds must be swapped, raw material feeds adjusted, and line tensions entirely recalibrated. Mathematically rigid programmed logic struggles to account for cascading, unpredictable physical variables. If a sensor reads an anomaly it isn't explicitly programmed to solve, the system halts. Automation can technically execute changeovers, but doing so requires highly optimized, inflexible, and expensive custom programming for every single product variation. The deterministic automation ecosystem stalls when it is forced to confront high-variance scenarios it was not explicitly programmed to solve. This brings us to the manpower model. In a factory context, manpower encompasses all human operational involvement, ranging from unskilled helpers to highly trained supervisors and technicians. Human labor remains heavily entrenched in advanced Indian factories, specifically for manual loading, visual inspection, and critical process adjustments. When a manufacturing line enters the changeover bottleneck, human intervention becomes the most effective way to restore stability.
A skilled human operator functions as an alternative, highly adaptive control loop. This separate flowchart on the right illustrates the human loop. When the system encounters a variance, the operator uses acute physical observation to detect the nuances of the disruption. Instead of applying rigid math, the operator filters these physical observations through years of accumulated historical experience and contextual judgment. This human processing is remarkably rapid. An experienced technician mentally cross-references past mechanical failures and undocumented machine quirks in seconds. In the execution phase, the operator rapidly applies a manual calibration or adjustment, stabilizing the line and successfully closing the human control loop. Achieving this level of adaptability through human labor is significantly more cost-efficient than writing the expensive custom code required to automate the exact same changeover. Manpower's ultimate engineering value on the factory floor is its heuristic ability to instantly manage unprogrammed variability through pure adaptability. This comparative model displays both of these architectures side by side as a single system. Automation is built to rely strictly on programmed intelligence and closed-loop systems to eliminate variability. Manpower is built to rely on human judgment, historical experience, and situational adaptability to manage variability. High operational costs often stem from plant managers misunderstanding this map. Automating high-variance tasks consumes capital without a clear return, while assigning humans to achieve strict zero-variance repeatability leads to fatigue and errors. Successful industrial engineering requires diagnosing a task's level of variance before assigning an architecture to it. The way operators apply this exact framework directly dictates the scaling capability and global competitiveness of Indian manufacturing. As AI-driven logic improves, machines will absorb more complex variables, and the boundary line between these two loops will shift. But the core foundational theories will remain. The future of Indian manufacturing is an ongoing optimization problem, built directly upon these two foundational architectures.